Hi, welcome back to my lecture. So today we move to the chapter 3, which is on lexical analysis and scanner generator. For our lecture today, for this video, so we will look into three subtopic, three sections, which is formal language, lexical tokens, implementation with finite state machines, and in next lecture we will look into lexical tables as well as lexical analysis with a scanner generator. Okay, first we want to look into what is a formal language, because when we doing with a lexical analysis, we need to understand what is a formal language. Okay, formal language actually consists of words whose letters are taken from an alphabet and are well formed according to the specific sets of rules. Means that they need sets of rules with the existence of alphabet. Okay, so what is alphabet? Alphabet can be symbols, it also can be letters, it also can be a token that we concatenate it, combine it into a string to become words. Okay, let's see what is a language element that build up, that develop a formal language. Okay, we need to be able to differentiate between a set and a string. Okay, before we go further into a lexical analysis, we need to know what is a set and what is a string. So a set is a collection of unique objects. Okay, we can illustrate a set as an array. Okay, so you imagine a set as an array. Okay, normally array will have a unique object, so you only list each element once. So the element may be listed in any order. You can put the object, the element in any order. Okay, and it also might contain infinite number of objects. Means that number of element might be infinite. A set also can have an empty set. For example, the set that contain no elements. So we call it as an empty set. So it is written in the forms of curly bracket, okay, open and close curly bracket, or it can be a symbol like a circle with a vertical line in the middle. Okay. And here is the examples of a set. The first one, we contain a set of 0 and 1. So we have a 3 string here, 0 is one set, is one string, 1 0 is another string, 1 0 1 1 is another string. Okay. The second one here is the empty set. Okay. The third one here is another examples of element inside the set, with the first element is the null string. So null string is represented using epsilon. This symbol is epsilon. Okay, a set also can be in the form of sentence, like number 4, the set of all strings of zeros and 1 having an even number of ones. Okay, so that is a set. What about a string? A string is a list of characters from a given alphabet. So what does it mean? Okay, let's look into the first example from a set here. The third string here, 1011. So 1011 is a string. So a string that is actually the combinations of characters. Okay. So the element of a string need not be unique. So it don't have to be unique. Okay. It can be duplicate, as you see in this example, 1011, they have a number 3 and number 1 occurs 3 times. The order in which they are listed is important. Okay, so for a string, the order is important because when you change 0, 1, 0, 0, let's say change it become 1, 1, 0, 1, the meaning will be different. It will represent different objects. So the order of the string is important. A string can also be no character and it is called null. This is what I said just now. Like example number 3, it is epsilon. We represent it using epsilon symbol. That is called null string. Okay. And the example of string is listed. We have 00, we can have 0011, we can have epsilon and others as well. So that is the difference between a set and a string. Okay, let's look into a finite state machine. So we use finite state machine actually to process our formal language. Okay, so that it can be processed by the compiler. So a finite state machine consists of a set of stats. Okay, and this stat actually includes starting stats and also a few accepting stats. Okay. Second one, a state transition function. We need to have a state transition function which consists of a state and also an input symbol. Okay, so input symbol actually is a given input alphabet, which is the string just now. It can be represented in two ways using a state diagram or a state table. Okay, so finite state machine can be represented into two ways, state diagram and state table. So this is examples of finite state machines. Okay. Here is the figure with the state and the transition function. This is the examples of finite state machine. So this machine is initially the starting state. Okay. The machine proceeds to a new state as indicated by the transition function. So we have here a starting state. A is a starting state. And between A and B, there is arrow here, arc here. This is what we call as a transition function, transition functions. Okay. On the top of the transition function, they have here numbers. That number is we call as input symbol. Okay, input symbol. Or sometimes they call it as input string. So this is A is the start state. The arc between A and B is a transitions functions. Number 1, the number on the top of the transition is an input string. So in this case, C is the accepting state. Okay, accepting state is represented using double circle. Okay. When the entire input string has been read, the machine is either in an accepting state, accepted, or in a non-accepting state, which is rejected. So what does it mean? When you have a input string, for example 1011 is your input string. When the time you come to the last digit of the input string, when the last digit of input string reach accepting state, in this case which is C, means that the input string is in accepting state. But if the last character of the input string ended at the non-accepting state, for example, maybe in A, maybe in B, maybe in D, so we say that input string is rejected, means it is non-accepting state. Okay. So the machine consists of state. A, B, C, D is a state. They have a transition function represented by the arc. Okay, the arrow is a transition functions. And accepting state, which is represented by double circle. We have a starting state represented by arc with no state at beginning. Input string is the alphabet. Okay, so this is roughly how the finite state machines looks like. Okay, as I mentioned, finite state machine can be represented in two ways, which is a state diagram, and the second one is a state table. So this is example. So the first one is the diagram. The second figure here is the state table. Okay, so this finite state machine actually represent a language. So what language does this finite state machine represent? So this machine represent L. L is a language. Okay, underneath here. L is a language. So what language? This machine accepts any strings of zeros and one which begin with 1 and ends with a 0. So this is the language for this machine. Okay. How to read? Okay, how to read the diagram or the state table? Okay. For example, between A to B. Okay, we want to go from state A to state B. How to read it? State A on input 1 goes to state B. That is how to read the representations. So what are the output that can be produced by this language? So the example here, 1, 0. So how to get 1, 0? You must start to read from a starting state, which is A. So 1, the first one you have 1 here. So 1 and then 0. Okay, so when you go to 0 here, from B to C is 0, so C is a setting state. So we say that input symbol 1, 0 is the output of the machine. Okay, what about 1, 1, 0? How to get 1, 1, 0? You have got 1 here, another 1 here, and then 0. So it ends with F setting state. So that is another language accepted by this machine, and you can do the rest. Any input symbols that can end at the accepting state is an accepted output string. Is an accepted output string. But if the input string ended at the non-accepting state, that input string is rejected from the machine. Then how to convert it into a state table? So we have A, B, C, D, 4 state here. So the first one must be a start state. Let's say your start state is B, it means that your state table also need to start with B. Okay, but in this case, it starts with A. So the one with asterisk here, C, on the C here, they got asterisk. Asterisk represent accepting state. Okay, so how to read it? From A, on input 0, it will goes to D. So here, A on input 0, it goes to D. A on input 1, it goes to B. So at this point, at this transition, on A on input 1 goes to B. Okay, that is how you convert a state diagram to state table. The same thing, you can convert a state table into a state diagram as well. Okay, so this is another example of a state diagram. So this finite state machine represent the language of machine accept any string of zeros and one which contain an even number of ones, which include the null string. Okay, this one also includes the null string as well. So the machine that can accept an even number of zeros and one, we call it as a parity checker. Parity checker is a machine that can accept even number of zeros and one. Okay. Okay, another term that you need to understand is about a deterministic finite state machine. So what is it? They have a deterministic and non-deterministic, but for your syllabus, we consider in this lecture, we will learn about a deterministic finite state machine. So what will be the difference? What is deterministic? There should be exactly one entry in each cell of the table. So what does it mean? Okay, for example, we focus on the state A here. Okay, state A. So how many outgoing edge or outgoing arc from state A to? Okay, this is the first outgoing edge. This is the second outgoing edge. So we look at the input symbol. Is the input symbol the same value or different? Okay, if it is the different value, so we call it deterministic. If the input symbol is the same, we call it as non-deterministic. So in this case, the machine is deterministic. Okay, it must be for all state that in the machine, for all states in the machine, must be all deterministic. Only then we say it is deterministic finite state machine. Okay. So again, the A here is the starting as well as the accepting state. Okay, and they only have two states here. Okay, some exercise for you to for you to try on. Okay, show a finite state machine in either state graph or table form for each of the following language. So does it mean state diagram or state table? That is what it's mean. Okay, so for each of the following language, in each case the input alphabet is 0 and 1. So only 0 and 1. So this machine only accepts 0 and 1. Okay, the first one, string containing an odd number of zeros. Okay, that's the first one. String containing 3 consecutive 1, string containing exactly 3 zeros, and string containing an odd number of zeros and even number of 1. Okay, so we see here is the solutions. Okay, the first one just now is string containing an odd number of zeros. So this finite state machine, the output should be odd number of 0. Okay, let's see the workthrough for this machine. You start with A. Okay, let's say you go A to A, which is 1. Okay, and then you go from A to B, which is 0, and you go from B to B itself, okay, which is the accepting states. So that that is number 1. But okay, that is number 1. So you got 1, 0, 1. So the number of 0 is odd, which is single number of 0. Okay, and then you start from, okay, another example, you start from A. From A you goes to B, from B you goes to A, and A you goes to B back, because the accepting state is B. So how many numbers of zeros? 3, right? So what does it mean is this machine will generate odd number of 0. It cannot produce even number of 0. Number one doesn't matter, because in the questions it only mentioned odd number of zeros. Okay, what about number 2? Number 2, it says string containing 3 consecutive 1. Okay, so we look at the 3 consecutive 1. So this machine will produce any string, but in each of the output string will have 3 consecutive 1. For example, we start with A go to B, B go to C, C go to D. So you have 1, 1, 1. If you said A goes to A goes to B, B goes to A goes to B again, and B go to C, and C goes to D, then also it has 3 consecutive 1. Yeah. Okay. The third one, string containing exactly 3 0, must be exactly 3 0, cannot less, cannot be more. So this is. So in this machine, let's say you go from A to B, B to C, C to D, it is 0 0 0. If you are doing a looping from A to A to A, then you go 0 0 0 again. Okay. All right. Next one, string containing an odd number of 0 and even number of 1. Okay, this is the fourth one. So this machine is odd number of 0 and even number of 1, right? Yes, even number of 1. Okay, so we can work through on these finite state machines. Okay, if you go from A to B, B to D, D to C, C to A to B again, then you have an even number of 1 and odd number of 0. You can count. You can do a walkthrough and try it by yourself. Okay, next one we will look into a regular expression. So what is regular expression? Regular expression is another way of writing language. Okay. Before this, you see that we can write a language in the form of a list, which is like an array. We can write a language in the form of sentences, machine that accept a string 0 and 1 that consists even number of 1 and even number of 0. That is in the form of sentences. Okay. And you also can write a language in the forms of regular expressions. Okay. So what is regular expressions? Okay. So regular expression is another method for specifying languages. So there are three possible operations: union, concatenation, and clean star. Okay, what is it? So the union is the operation on language is designated with a plus symbol. Okay, so plus symbol indicate union. For example, the first example there you have a list of A, B, C, A, B, and B, A, and you concatenate it with a list of B, A, and B, B. So what would you get is a list of A, B, C, A, B, B, A, and B, B. So you would remove any duplicate string. Okay, so this is the output for concatenation, the union. Okay. Example 2, if you have a language plus an empty string, so what will be the output? The language itself. Okay, so nothing. You are adding to empty string means that you will get the language itself, the first language. The concatenation is designed by the rest dot. Dot would mean multiplication or mean concatenation. So for example, the first one, ABC dot BA. So when you concatenate, it becomes ABC, BA. Second one, when you concatenate S with epsilon, noun string, the result that you get is S. Okay. The third one, if you concatenate two lists, AB, AC, concatenate with B and noun string, so you need to do some kind like a product. Okay, AB with B, AB with epsilon, A with B, A with epsilon, C with B, C with epsilon, like a product. So any input symbol that concatenate with epsilon, then you will have the input itself, which go into the example number 2. So this is the string that you get, because any string that concatenate with epsilon, then it will return the string itself. Example number 4, language that concatenate with the epsilon noun string equals to L, but if the language is concatenate with the empty string, then you will get the result as empty. When you product it with the empty, you will get empty. What about the clean star? Clean is a unary operations, okay, by its own. Okay, they don't have two operand, they're only by its own unary operations. So designated by apostrophe asterisk. So clean star, they use asterisk as a symbol, and it's often closure. Sometimes it's called closure. Okay. For example, 0 plus 1, and in the bracket they got a star as a superscript. This is called clean closure. So what this star mean? Star would mean the occurrence of that input symbol 0 or more times. That's what it means. Okay, so in this case, it would be if we say that star is n, and n could be 0, n could be 1, can be 2. So let's say we say that n is 1, then the output that you get is 0, 1. If you say the star n is 2, okay, the L is 2, L2, then the output that you get is 0, 0, 0, 1, 1, 0, 1, 1. Okay. If you say that the star is 3, then you will get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 0, 1, 1, 1. Okay, it depends. Yeah? Okay, it can be reproduced until infinite number, because the star here represent 0 or more. Yeah, represent 0 or more. Okay, exercise. For each of the following regular expressions, list 6 string, at least 6 string, yeah, which are in its language. For example, A, B plus C, star, star, D. So what does it mean here? So this would mean B plus C got a star here, and the whole thing here got also star, and then D. Okay, so look into the first one. Okay, so it can get D. So how they can get D? So when they get D, it means that it will assume this star is 0. So that's why you only get D. Okay, AD. So A from here, so means that this star is 1. Okay, this star is 0. So they get AD, and so on. Okay, you can try to generate the strings by your own and see what you get. Okay, so try also to find out what is the simplest string generated from the above language, from this language. For example, the first one, the simplest one would be D. Okay, so when you assume the star is 0, then the simplest string that you get from this regular expression, this language, is D. Okay, try to do the second one and third one as well on your own. Okay, then we look into a lexical token. So lexical token is the first phase of a compiler. Okay, it's under the first phase of compiler, which we call it as lexical analysis. So it also been called as lexical scanner. We also call it lexical scanner. So lexical analysis attempt to isolate the word in an input string. Okay, so we want to split it into words, the input strings. So a word, also known as lexeme, a lexical item or lexical token. Okay, that is how we normally call our words. Sometimes we call it as a token, sometimes lexeme, sometimes lexical item. Okay, so here is example of word. Words can be many in a programming language. So this is the types of words. So they have a class, they call it token class. They number it between 1 to 9. That's number. Okay. So the first word is for a reserved word, which is like while, if, else, for, okay, which are not available to programmer to use. So you cannot use it because it's a reserved words. Okay. The second one is identifier. So this word actually is for programmer to construct, to use it in your program, like you want to use it for your identifier, for your variable name, for your method name, function name, something like that. That is identifier. Means that the programmer created it. The third token class is operator. So the operator is any symbols, character, arithmetic operator, logical operator, and so on. The fourth class is a numeric constant, so numbers such as 124, 120.35. Okay, so this must be converted to a numeric format. Okay, bear in mind when you do a lexical analysis, we assume all input string as a string, all input as a string or a character. So what is numeric constants may be stored in the table. So anything that you store in the table is a string. So we call it as a numeric constant. A numeric constant actually is the string. But when we want to manipulate the number, we need to convert the type into a numeric format later. Okay, but when you store inside the table, it is called numeric constants. Class number 5 is a character constants, okay, single character or string of character enclosed in quote. So we call it as a character constant when a string character that enclosed with a quote. 6 is a special character, okay, such as any symbol, any delimiters, bracket, comma, okay. This generally is a single character. Number 7 is comments, okay. Comment is also a word, but in a free format language, it is omitted or it is ignored by the compiler. So it is not counted as token because it is ignored. The same thing with 8 and 7. 8 and 7 also is a word, but it is ignored by the compiler and is not counted as the token. It's not counted as a token. Okay, so white space as well is not counted as a token, new line as well. So there are 9 token class altogether that you need to know. So what is the purpose for you to know? Why you need to know? Because you need to create a table for the symbols. Okay, for example, you have a while statement like this. Okay, so you need to split this into a token. Okay, so after you splitting into a token, then you need to state what is the token class so that you can create a table something like down here. So this is a table. So you need the compiler, the lexical analyzer, not you, the lexical analyzer actually will convert this information into this table. Okay, so that is how the lexical analyzer do tokenization. So they split it into tokens. So while actually under the class 1, okay, so a token value, so they have a token class. This is the token value is code for while. The bracket here is actually a 6 on the token class number 6. Okay, token class number 6 is a special character. Okay, so there's a code for bracket. And x33, so this is a pointer to symbol table entry for x33, so it is under class number 2. Okay, it is identifier because this is the name that the programmer gave, so that is the identifier, and so on. But the tokenization will end at the semicolon. So this the comment here, the comment at the end here will be ignored by the lexical analyzer. So your table only will contain information up to semicolon in this case. So comment, white space, and new line is ignored by the lexical analyzer. So this is the table created from the lexical analyzer. Okay, the first phase of the compiler. So this is a table created. Okay, now we look into the implementations with a finite state machines. Okay, so we have seen this is a finite state machine to add. This is the finite state machine to accept identifiers. Okay, identifiers is a name that are given by the programmer for identifying variables, function names, and so on. So this is the example, the example of machine that accept identifiers from the start states. And they have L is the alphabet, okay, D is the digit. Okay, so this is only the example how they do the finite state machine to accept identifiers. Okay, the second one is the machine that will accept a numeric constants. So this is also an example. What kinds of numeric constant that can be accepted by the machines? So they have designed this machine to actually to provide a rules of what digit that can be accepted by the machine. Okay, so the machine, the input that is not past this machine, we will say that the string is rejected. It's not the numeric constant that accepted by the language. Okay. Okay, this is another example of finite state machine to accept keywords. We know that in programming language they have lots of keywords. So this machine can accept if keywords. Okay, the first one here, if. It also can accept an import, import, and also accept integer. Okay, so and so on. So this machine is used to pass to check for keywords. If it can end with the specified input correctly, then it is a non-compile error. Okay, that is how they use a finite state machine to check whether your system, your program, not your system, your programming language contain a syntax error or not. So they will scan each of this character, like if they scan from I to F. Is it end with the accepting state? If yes, then no syntax error. But if it ends with non-accepting state, then it will say there is a syntax error. Okay, for example, let's say I change it IFR. So I go through this machine, I pass the input into this machine, so from I go to F, but I have another string there, R. So it does not end there, but in my machine, I don't have any outgoing edge that have input R. So the machine automatically will say IFR rejected, means that there is a compilations error. So that is how they check for syntax error. Yeah. So under the implementations, the machine not only divide the string into token, the input string into token, not only specifying the token class, okay, but the analyzer also need to know the actions. If it is the string from A to B, so what would be the actions? The action here would mean the method, which method to provoke, which method to infer. Okay, so that is actions. Action is about telling the analyzer, you need to put the informations in the table that we see just now. What are the actions to be taken? Okay, for example, in this case, when we want to go from the start state to another state here, on input A, you need to do P1, P. P here is a method. So what is a P method? So the system need to compute, need to process this P method. So this is the P method that the system need to compute. So the transition functions also will tell you not only what input, but will also tell you what action to perform. So what action, it means that what method to perform. So that is what we call the implementations of finite state machines. Okay. So for this reason, we wish to associate an action or function to be invoked. For what function to be invoked, with each state transition in the finite state machine. So every transition function, they need to tell what is the method. Okay, associate an action with each state transition in the finite state machine. Okay, so for each state, for each transition function, they need to have a action, which is a method. Okay, so that is the three sections in the chapter 3. Okay, on the next sections, we will look into a lexical tables. So we will look into the lexical tables in the next lecture. Okay, thank you very much.